Okay, so this is what you should see when you graph it. What kind of, well, let's ask, does the limit exist as x goes to 0? How come? There's a jump, okay? That means when I go from one side, if I approach from the left, what would the limit be if I was on the left side of the graph? What do you think it would be trying to tell me on the left side? -1. If I was on the right side, what would it be trying to tell me? 1. They don't agree. And you can see in the table over here, same thing. On the left side, I'm at -1. On the right side, I'm at +1. Those two things, you know, they're not approaching the same number, so the limit does not exist. Okay? But let's take a look at how we could do this algebraically as well. Okay, so here was the graph. Whoops. So algebraically, the way we could do this is we have to use a piecewise graph. So if we think about the way this works, the absolute value of x, we talked about that in two pieces, right? We said that's like -x if x is less than 0, and +x when x is greater than or equal to 0. So now I can actually do this without a calculator or a graph if I show you the piecewise version of this function. So here's the piecewise version. It's going to be -x divided by x when x is less than 0. And it's going to be x over x when x is greater than or equal to 0. Okay, and obviously we could also call that -1. We could call that +1. They would still simplify like we normally would. So that means on one side of the graph, the limit as I approach is going to be this one. As I approach from the left, it's going to be -1. As I approach from the right, it's going to be +1. Okay. So we're going to practice more algebraically, but that just gives you an idea of where we're headed. We could show that this graph does not have a limit without the picture. Okay. And again, we'll spend a day on, well, we'll spend next block actually, since we're in double block today, talking about how to do it algebraically. So all I want to do now is test your concept. Sorry, Eamon. Say it, don't spray it, right? I just want to see conceptually if you understand what a limit is. So these next two examples, let's just start with question number 1 that says, for the graph g of x shown here, so this is g of x, find the following limits as x goes to 1, as x goes to 2, and as x goes to 3. Okay, so I want you to actually discuss this with your neighbors. Say what you think each of those 3 limits are to your neighbor, and be prepared to support your answer. Okay, some good discussions. Let's hear. What do you think? How about limit as x goes to 1? It does not exist. As I approach for 1, okay, as I'm looking at this spot here, they don't agree. One limit is going to the wrong spot as the other, so there is no limit here. So I'll put does not exist. Because one side is trying to tell us the value is a 1, the other side is trying to tell us it's a 0. Okay, how about at x equals to 2, what's the limit as x approaches 2? Yeah, so whether I go from this side or I go from this side, I end up at the value 1. They both agree it equals to 1. Okay, so for the last one, hands up if you think the limit exists. Just the limit exists, not what I'm going to ask you what it is. Does it exist? Okay, hands up if you think it does not exist. Okay, so remember the definition for a limit. Do you actually go to the value itself? No, you do not. So this is a distraction here. From the point of view of a limit, that does not exist at x equals 3 because we're not actually going to the value itself. We're going as close as we want and as close as we want, but we're not actually touching 3. So we'd be at 2.999999999999999 and maybe a couple more 9. But we don't actually touch 3. So according to the limit, what's the value? 0 is correct. So the value here for the limit is a 0 because I don't actually touch the point. If I was saying what's the value of this function at x equals 3, the function equals 1 because that right there is the value of the function. Okay, so remember there's a small distinction. For a limit, you can get as close as you want, but you don't actually need to touch the value itself. Okay, so try it again on this example. See what you can come up with. Okay, let's try and recap here. At -2, what's the value of the second function? Or sorry, let me be more specific. What's the value of the limit as t goes to -2? Right, so this one exists. It equals to 0. The value as t goes to -1. Yeah, it'd be -1 right here. So that's fine. And as it goes to 0, what do you think? Hang on. By nothing, do you mean 0? Doesn't exist, right. This does not exist because there's a jump. From one side, it says I'm going to 1. From the other side, it says I'm going to -1. Okay? Remember, this is the value of the function. This is f of t. Okay? I'm looking at the limit. I'm not going to touch the value itself. I am looking at the limit as I approach the value. Okay, so let's we're going to briefly discuss the formal definition of a limit. And to do that, we're going to play a little game here to give you an idea before we actually look at the formal definition. So I actually have an applet for this that I'm going to show you because it's much easier to do this with an applet. So let's take a look here. Okay, so I believe that's the same one as your notes. Oh, 2x minus 1, sorry. And so we're going to look at the value as x approaches 4. And what do you think the limit is going to be? I mean, we can substitute it in. That's going to be a 7, right, if we substitute in x equals 4. So here's what I'm going to put in is I'm going to put in, I want x to go to 4. The value of the graph would be 7. And I have to fix this picture because I can't see anything. Okay, so x equals 4. Did I not do that right? Let me check again. That's the problem. So let's go from -1 to 6 and -1 to 10. Okay, so I'm going to zoom in on this graph a little bit right there. Maybe a bit more. Okay, so here's the way this game is played for what the actual definition of a limit is. Because we don't actually have to be defined at the value itself, we have to guarantee that however close you want to get, I can produce a value that will get you there. So for example, in this one, what this box is showing you is it's saying if you want to be within 0.1 of the actual value 7, you will need to be within 0.05 of the value 4. For example, at 4.05, this is the value here, which is at 7.1. I'm still within the bounds. Okay, for example, if I gave you too much space and I said, oh, well, yeah, here, I'll give you to, I don't know, let's say 0.5. Okay, well, now I'm all off the chart because I'll put in a value. I'm supposed to be at 0.1 and I'm way off the charts here. So it's not accurate enough to get me within 0.1 of the actual value. Okay, so for example, if I was to try this one, let's say you wanted to be within 0.4, okay, then in this example, I'm going to need to be within 0.2 of the value of 4 to get me within 0.4 of the value 7. So the game is trying to figure out, okay, I don't have to go right to 4. How close do I have to go to 4? Okay, so somebody give me an accuracy that's not like ridiculous, like 0.000000001. Give me an accuracy that we can try this with. How close do you want me to be to 7? 2 decimal places, so that would be 0.005. Okay? Now, I'm going to have to zoom in, of course, because that's a pretty small number. Okay, so if I'm going to be between 7.005 and 6.995, how close to 4 will I have to be in order to play this game? For example, at 4.1, would I fall outside of that range, or am I still in that range? I would fall out of that range. So I'll just show you here. If we tried it at 4.1, it would be 2 times 4.1 minus 1. So 8.2 minus 1, that would be 7.2. I'd be out of the range. So Andy has asked that I be within 0.005. Okay? So how close do I have to get in order to meet Andy's requirement? Sure, Alan? Right, so you may have just, you figure out the pattern, or do you have a better idea? Did you figure out the pattern, or kind of? Okay. So I'm going to show you why it is that it works at 0.0025, but there's that box, and the box is trying to show you again, the yellow marks are showing you how high you can go. In this case, you can go 0.005 of height. How wide am I allowed to be away from 4? I'm allowed to be 0.0025 of width away from 4. Okay? You could be less. It would be fine for somebody to say, oh, no problem. If you want to be closer, make it 0.005. That will work. The box is still close enough now that it will work. But it's probably the strangest part of calculus that we'll deal with, because this is the conceptual way of talking about a limit. And even at the end of the semester, after you've done all kinds of crazy things, people still say, man, that epsilon delta stuff is so weird. So I'm going to show you the way that you actually prove a limit. And then this is the game I was talking about. We call it epsilon delta proofs in math. So here's what the math looks like. It says, if I want to prove that the limit as f of x goes to some value is L, okay, this is what I want to prove. Then here's the conditions that I have to show are true. Okay. So the first condition says that I have to be within the value delta of c. So that means, for our example, it was the number 4. You might tell me, like Andy said, 0.005, so I'd have to be at 4.0025. This is how far away from the number I can be. The second example is for how far from the limit you want me to be. So this is within epsilon, and we'll have to continue after the break, of the limit. Okay, so we'll talk about this more after the break.